In this video, I'm going to show you some more examples of solving equations. And this set of videos is going to focus on the fact that we can use identities to help us solve equations as well. So here's an example, and I see 2 cosine squared x plus 3 sine x equals 0. And I see a square there, so maybe I think about my usual techniques. Well, can I factor something, or can I use a square root here? And I really don't see how I could factor anything. Cosine and sine, I see 2's and 3's. So there's nothing that's jumping out at me. And what I can do here is I can actually use a identity to make this a little bit easier. So I'm going to use an identity on the cosine squared piece. And again, you want to remember that, well, sine squared plus cosine squared equals 1. And if I solve for cosine squared by subtracting that sine x to the other side, I can replace cosine squared x with 1 minus sine squared x. So I'm going to go ahead and do that. And that's going to be helpful because then I'll have everything in terms of sine here, which will make things a little bit easier. So I have 2 times 1 minus sine squared x plus 3 sine x equals 0. And of course, don't forget your restriction. We'll come back to that later. I'm going to go ahead and distribute that 2. So I have 2 minus 2 sine squared x plus 3 sine x equals 0. I'm also going to rearrange this. Usually when I have squares, we'd like to write them first. It looks like I have a first and a middle term that's coming into play here. I'm going to rewrite this. Negative 2 sine squared x plus 3 sine x plus 2 equals 0. So I just swap these, swap this piece to the front and move this 2 to the back. And then the next thing I'm going to do to clean this up is I actually am going to multiply both sides by negative 1. And that's because personally, I just don't like having a negative square term, but that's just a personal preference. So this becomes 2 sine squared x minus 3 sine x minus 2 equals 0. Now I actually see something that I can factor. And again, if you don't see it right away, try just replacing the sine x's with u's or x's. And it looks like 2u squared minus 3u minus 2 equals 0. And you can think about, well, how could I potentially factor that? And let's see, 2u plus 1, and then u minus 2, I think will be the final case. Let's check it. There's the 2u squared. Negative 4 plus 1u is negative 3, and then there's negative 2. So it's often easier just to kind of factor it in a more basic form first. And then I'm going to use the same factorization here, but instead of writing u, I'll write sine x, excuse me. All right, now I have something factored. I'm going to set each factor equal to 0 and solve. Again, remember when we're factoring, we do need that right side equals 0. So 2 sine x plus 1 equals 0. Sine x minus 2 equals 0. I'm going to get the sine x's by themselves. So I'm going to subtract 1 here. And then I'm going to go ahead and divide by 2. Here, I'm just going to add 2 to both sides, and I have sine x is equal to 2. Now, on the right side here, this one has no solution. It's just the regular sine function, and if you remember, sine goes between negative 1 and positive 1, so sine x equals 2 is not going to happen. And if you're not sure, again, always graph. You can graph the sine function and look at it, and you'll see that it will never touch 2. So that one is out. And then for the left one here, we do have to figure this one out. It definitely does have a value of negative 1/2 at some point. And do I have it close by? Let's see. So I'm using my notebook here, but this is why I encourage you guys just to kind of keep little note cards with you or use the inside or outside cover of your notebook, and then you have this stuff easily accessible rather than flipping through like I'm doing now. So I have my sine chart. I'm looking for negative 1/2, so I see it there, and then I also see it here. So those are going to be my 2 values, and here is between 0 and 2 pi. Okay, Like in the last videos, technically you have more answers than this, right? Because sine does have a period of 2 pi. So what you could do is add that 2 pi n to each one. However, we have a restriction here that we're only looking at the first period. So if you run through that, the n equals 0 is the only one that matters here. And these are the only two values that are going to occur within that domain restriction. So these will be our final two answers. But again, just remember, you're always adding that period, right? So here the period is 2 pi, and then you're multiplying it by n. So that gives all values of solutions, but again, here we just want between 0 and 2 pi. So that's why I only need these two answers in this case. All right, let's try another one. All right, be a little careful here. This looks like almost the same problem as the last example, which is why I like it, but it's a little different. The last one was cosine squared x. This is cosine 2x. So be really careful there, because if I know I read it first, I was like, hey, we're doing the same problem again, but we're not. This one is slightly different. Same domain restriction with that 0 to 2 pi, but it's cosine 2x. Take a look at the last one. That was 2 cosine squared x. So again, a little bit different. So here I'm going to make a substitution. Again, I don't really see how I can work with cosines and sines together here. I don't see anything obvious. So we're going to use an identity. And here we can use the double, one of our double angle identities here. So we're going to use the one that is cosine of 2x equals 1 minus 2 sine squared x. So I'm going to go ahead and make that substitution. I get 1 minus 2 sine squared x plus 3 sine x minus 2 equals 0. I'm going to combine my numbers here, my like terms. And then like before, I am going to multiply everything through by -1. I just personally don't like having a negative square term. I find it more difficult to work with. So I like to get rid of it. Now I see something that looks like more of a normal quadratic, right? So something with like a square and then a middle term. And if you find it helpful, you can go ahead and substitute out that sign piece just for, I don't care what letter you use, U or X or something, just so you can see what the regular form looks like. And then you can work on factoring it that way. And if you do that, it factors as 2u minus 1 and u minus 1. So I'm going to rewrite this, and I'm going to use u's though. I will use sine. So 2 sine x minus 1 times sine x minus 1 equals 0. Remember, with factoring, you want that right side to be 0. And now that everything is factored, I can set each piece equals 0 and solve. On the left side, we're going to add 1 to both sides, and then we're going to divide by 2. And when we do that, we get sine x equals 1/2. And over here, I'm going to add 1 to both sides, and I get sine x equals 1. Now, I left my chart out, which was smart this time. I'm only going between 0 and 2 pi here, and luckily my chart goes between 0 and 2 pi already. And again, I'm not plugging anything in, right? It's just basic sine x, so I have that chart I can use. And for the first one at 1/2, I see pi over 6, and I see 5 pi over 6 here. And then for 1, I see pi over 2. I wrote 1 again. X is equal to pi over 2. Sorry, I was writing the answer of 1 there. So the angle there was pi over 2. So I have 3 solutions here. These are all 3, again, because we're restricted here from 0 to 2 pi. So just like with the last example, I won't write it out, but if you don't have the restriction, remember you're adding in the period. So plus, in this case, 2 pi n, cosine and sine, or here sine has period 2 pi. But because we're only within the first period, these are all my answers. So we are done. Okay, so the n equals 0 would be the only answers. And you do see a lot of restricted domains. Again, because everything oscillates and repeats, a lot of times having just the values for one period is significant, and that's enough. So you see a lot of restricted domains when we're solving equations. Now, here's an example where we are going to use an identity, but it's not quite ready yet. So hopefully this is kind of looking a little bit familiar, but what happens is it's missing a piece. If I multiply both sides by 2, what I end up getting is 2 sine x cosine x is equal to 1. And then hopefully, if you remember back, this is a double angle formula. This is the double angle formula for sine. So sine of 2x is equal to 2 sine x cosine x. So we're able to go ahead and make that substitution in there. So I have that sine of 2x equals 1. Now here, this one's a little bit more complicated. It's not just sine x, it's sine of 2x. So if I go to my chart, I know that sine theta is equal to 1. We just saw this right here. When theta is equal to pi over 2. Now, again, my theta is not just x, or else it'd be pretty straightforward. It's 2x. So I'm actually solving for 2x equals pi over 2. But remember here that the period for sine is 2 pi. I do have to add in that 2 pi n before I solve. Here to solve, we're going to divide by 2 on both sides, or you can think of it as multiplying by 1/2. Make sure you go ahead and distribute through. So x is equal to pi over 4 plus those 2's will cancel here. And we're just left with pi n, or n pi is fine as well. Now we're basically done, but we have a restricted domain. So they don't want us to write all the answers like this. They want us to actually go ahead and figure it out. So your first one is going to be n equals 0. So in that case, our x is just pi over 4. That's obviously going to be in this domain right here. Next, I'm going to try n equals 1. So I have pi over 4 plus pi times 1 for the n value. So pi over 4 plus pi is going to give me 5 pi over 4. So this is my next x value. That is less than 2 pi, so that's fine. I'm going to try n equals 2 here. So I get pi over 4 plus pi times 2. Now this is going to be too big because you're adding 2 pi, and the highest value, actually 2 pi is already above. So this is going to be too big. So in this case here, we only have 2 solutions. We have the solution of pi over 4, and we have the second solution of 5 pi over. So watch out for these. Again, they get tough when you don't just have an x on the inside, because you can find the angle, but it's not just x equals, it's 2x equals. And then you also have to take the period into account as well. So those are the trickiest ones, I think, because they're easy to miss and just think you're done once you have that pi over 2. But if there's any change to the value inside the angle here like this, where it's being multiplied by 2 or another factor, you do have to take that into account and make sure you solve that piece. All right, let's do one more in this video. Okay, now this one is probably one of the hardest ones because there's really nothing that I see that is helpful, right? I can't factor this. I can't really solve anything. I see this one. I don't really see an identity that's going to work here. Like I don't have a double angle formula. I don't have a half angle formula. I don't have a power reducing formula. I don't have one of my Pythagorean identities. It's kind of like what's going on. So in something like this, we're going to do a pretty good manipulation. It'd be really nice if this was sine squared plus cosine squared, because then it's equal to 1, right? So what we're going to do is we're going to try something, and we're actually going to square both sides, hoping that we can then use the idea that sine squared plus cosine squared equals 1, and that will help us out. So again, this one is really hard because there's nothing naturally pointing you to really do this. It's sort of like a guess with the fact that this is kind of close to the Pythagorean identity. So let's maybe try making it happen. So we are going to square both sides here. Now, when you're squaring the left side, don't forget you do have to multiply it out. It's not sine squared minus cosine squared. It's sine x minus cosine x times sine x minus cosine x. Now, 1 squared is just 1, so that part's easy. But here you have to multiply. Sine times sine is sine squared minus sine times cosine minus another sine times cosine. Negative, negative becomes positive, and then you have cosine times cosine is cosine squared. Now in the middle here, we can combine these, and I'm also going to move the cosine squared up here because I know that these two are going to add together to become 1. I have 2 of these, so it becomes minus 2 instead. Now, this here is the Pythagorean identity. Sine squared plus cosine squared equals 1. I'm going to keep solving here. I'm going to subtract 1 from both sides. So I have negative 2 sine x cosine x equals 0. I'm going to divide out this negative 2. It's not really doing anything for me. And when I divide it out of both sides, 0 divided by negative 2 is still 0. So I've cleaned this up as much as I can at this point. I don't know if it really has helped me too much, but what I do see now is I do see 2 things being multiplied equal to 0. So I have 2 factors that are multiplied equal to 0. And when that happens, I can split. So sine x equals 0, right? This being multiplied. And then cosine x equals 0. Now we're going from 0 to 2 pi here. So I do have charts already made from 0 to 2 pi, which is really helpful. So for the first one, well, for sine, I have it out, so let's just use it. You get 0 at 0, also at pi, and then again at 2 pi, but 2 pi is too big, right? It's outside that range, or that domain. So it's 0 and just pi. And then you can do the same thing for cosine. I won't take out that chart, but for cosine, you get 0 when x is equal to pi over 2, and then also 3 pi over 2. Now, for both of these, you have period of 2 pi. So remember, you could always add 2 pi n to all of these solutions here. But in this case, we don't really need to do that because we're restricted to 2 pi. And I already had my tables created through 2 pi as well. So I know I've already looked at all possibilities. But again, if you're not sure, you can always get in the habit of adding that period part in, plugging in n equals 0, n equals 1, and so on, and checking. If you plug in n equals 1, it becomes too big. So the initial answers are the ones that are going to be our solution here. Now, before we end here, I will say that I'm getting ahead of myself because I was excited. I'm like, sweet, we're done. We're ready to move on. And I forgot something really important. So I paused the video. I said, wait a second, I'm forgetting something here. Even I forget things. I get excited. I think, oh, I'm done. I'm ready to move on. But I forgot when we square both sides of an equation, the idea of squaring things or cubing them, or if I multiply by x's on both sides, Anytime I'm multiplying with x's on both sides, there's always a chance that I'm creating extra solutions. And you're probably used to this when you have roots. So for instance, if I was solving like square root of x is equal to 5, we have that process of squaring both sides like we did here. When you have something like that, you always have to check your solutions because it is possible to get what are called extraneous solutions. And extraneous solutions basically don't work. So they come out to be final answers, but when you check them, they don't actually work. And that's what I was forgetting to do here. And it's a really important step. And like I said, I forget this too, because sometimes I'm like, oh, sweet, I'm done, I can move on. But if you are squaring both sides or cubing both sides or multiplying by x on both sides, anything like that, you do need to check your answers because it is possible that you created an extra solution by accident or more than one. So these are my initial 4 answers, and I do need to check my solutions here. So I'll just check each one. Now, when you check, go back to the original equation. That's really important that you don't check later on. You have to check in the original equation. So if I check x equals 0, I plug it in. Well, sine 0 minus cosine 0, is that equal to 1? Sine 0 is 0. Cosine 0 is 1. I get negative 1 equals 1. This is false. This does not work. So actually 0 is not a true solution. I check pi, sine pi minus cosine pi, is that equal to 1? Well, sine pi is also 0. Cosine pi is negative 1. And again, you would just use your charts here for those values. Negatives cancel, I do get 1 equals 1, so this one is good. So pi will stay. All right, here I check sine of pi over 2 minus cosine of pi over 2. Is that equal to 1? Well, sine of pi over 2 is 1, and cosine of pi over 2 is 0. So 1 equals 1. This one is good. So far we only have one problem. And let's check the last one. All right, sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. I get negative 1 equals 1, and this is not true. So actually, this one needs to get thrown out as well. So I'm glad I checked here, because a lot of times, if we don't check, sometimes they all work and it's fine and you don't notice anything, and you kind of luck out. Other times when we check and we may have 1 or 2 or multiple, whatever it is, that don't work. So actually, the only real solutions here are x equals pi and pi over 2. And the other 2 are actually extraneous. So they're not solutions at all. They come up because when we square both sides, you basically kind of creating extra x's in a way. So you're getting extra answers sometimes. It doesn't always happen sometimes. So here's one where I'm glad I didn't end the video and forget. You could probably see to my face, I was like, something's not right here. And it was because I forgot to check. So if you're squaring, cubing, raising to any power, or if you're multiplying like by x on both sides or sine x on both sides, cosine x on both sides, anything like that, then you do have to check your answers. It's always a good idea to check anyway, but in those cases, you really do need to check to make sure there are no extraneous solutions there. All right, I think that is finally the end of this video. All right, thanks guys.